In this problem, we're looking at a tank with a mixture of water and sugar. So we have a tank that contains 800 liters of pure water, a solution that contains 0.05 kilograms of sugar per liter enters the tank at the rate of 10 liters per minute, and the solution is mixed and drains from the tank at the same rate. So our first question is, how much sugar is in the tank at the beginning? Well, we have here, it says pure water in the tank. So at the beginning, we've got no sugar. So how can we write that? So if we have S of t being the amount of sugar in the tank at time t, then we can write this as S of 0 equals 0. So at the beginning, when the time elapsed is 0 minutes, we've got 0 kilograms of sugar in the tank. So that's our initial condition. Alright, let's look at part B. So with S representing the amount of sugar in kilograms at time t in minutes, write a differential equation which models this situation. So we wanted to model how the amount of sugar in the tank is changing over time. So that's going to be given by the equation for ds over dt. So it might help first to think about what are the units of this going to be. Well, S is the amount of sugar is given in kilograms, and then the time t is given in minutes, so my units are going to be kilograms per minute. And how can we think about how the amount of sugar is changing? So we have to think about there's sugar coming in, and then there's sugar going out, so we want to take the sugar coming in and subtract the sugar going out. Alright, so what are those? So coming in, we've got 10 liters of solution per minute coming in, and in that solution we've got 0.05 kilograms of sugar per liter. So we can cancel our liters here, and if we multiply these together, we have 0.05 times 10 kilograms per minute coming in. Alright, what about going out? Well, going out, we've got 10 liters being pumped out of the tank every minute, and that's 10 liters out of 800 liters total in the tank. And so that's going to give the fraction of sugar that is being pumped out is 10 over 800 times the total amount of sugar in the tank at the time, which is S. And that's also kilograms per minute. Alright, so let's rewrite that a little bit nicer. So multiplying 0.05 by 10, that is 0.5 minus, and then I can simplify my fraction here, that's the same as 1 over 80 S. So that's my differential equation. ds over dt is equal to 0.5 minus 1 over 80 S. So next, we want to find the amount of sugar in kilograms after t minutes. So we want to find the equation for S of t. And we had our differential equation, ds over dt is equal to 0.5 minus 1 over 80 S. And this is a separable differential equation, so we can solve it. And the first thing I want to do is I want to pull out this 1 over 80 here from in front of the S. So if I'm pulling out a 1 over 80, I need to multiply everything inside times 80. So 80 times 0.5 is going to be 40. And then minus 80 times 1 over 80 is 1, so I've just got 1s there. Alright, that's still ds over dt, and now I want to pull all my s's over to the left hand side and my t's over to the right hand side. So first I'm going to divide by this 40 minus s on the left. So 1 over 40 minus s ds, and then I'm going to multiply by dt to get rid of that and pull it over to the right. I'm going to have 1 over 80 dt. Okay, now I can go ahead and integrate both sides. So on the left hand side, this is a natural log, and since I've got this minus s in here, this is when I integrate, I'm going to get negative of the natural log of 40 minus s. And then on the right hand side, I'm integrating a constant, so I'm just going to get 1 over 80 times t plus my constant of integration c. Okay, and let's look at that more on the next slide. So this is where I am so far, and now I want to solve for s. So the first thing I want to do, I'll get rid of this negative here. So then I'll have the natural log of 40 minus s is equal to, multiplying this side by negative 1 over 80t minus c. And now I want to get rid of my natural log, so I'm going to exponentiate both sides. So on the left, I'll just have 40 minus s, and on the right, I'll have e raised to this whole quantity here, negative 1 over 80t minus c. Now I'm going to do a little trick here. I can rewrite this as e to the negative 1 over 80t, and then pull this part out. This is times e to the minus c. And e to the minus c is also a constant, so I'm going to rename this and call it k. So I'll have 40 minus s is equal to, and I'm going to pull it in front here, k times e to the negative 1 over 80t. Alright, so we're getting close here. I just need to move the 40 over to this side. So negative s equals k e to the minus 1 over 80t minus 40. And then multiply by negative 1. S is equal to negative k e to the minus 1 over 80t plus 40. Alright, so we've got a formula for s, but I've still got my k in here, so to figure out what k is, I need to use my initial condition, which was s of 0 is equal to 0. So that means if I plug in 0 for t, I should have 0 on the left hand side, so I should have 0 is equal to negative k. Alright, so if t is 0, then e to the 0 is equal to 1, so I've just got my negative k here plus 40. So what does that mean? That means that negative k is equal to negative 40, or k is equal to 40. So I can write my equation, s of t is equal to negative k, negative 40, e to the minus 1 over 80 t plus 40. So I've got my equation for the amount of sugar after t minutes. And just to check, you can go ahead and plug back in 0, make sure you get the right thing. So if I plug in 0, this e to the power is going to be 1, so negative 40 plus 40 is 0, and that satisfies my initial condition. And finally, for the last part, we want to find the amount of sugar after 20 minutes, so that's going to be s of 20, and I just plug that into my equation at negative 40 e to the minus 1 over 80 times t is 20 plus 40. And if I work that out, that is about 8.8480 kilograms of sugar in my 800-liter tank after 20 minutes.